What else? Form. Let's take it away. I just stated that I didn't prove that formally, but that's what happened. Okay. Now, how did we say those standing waves can form? I'll try to draw them in here. I can have one standing wave like this. Okay. And then I can have another standing wave like something like that. Actually, it'd be this. It's not quite like that. But this will. That's actually a bad drawing for the. You'll get the picture of it. So what's going to happen here? Depending on where you have the particle. Actually, let me. I don't like this at all. I'm going to draw that to the wave function square. So if I draw the wave function square, you try doing that with PowerPoint. Yeah. Okay. So if I look at the wave function squared, you'd have something that looks more like this. You know, this guy. You can't see it on this.
It's kind of like balanced along the.
Yeah, you basically you can have the wave that's going to peak here, or you can have the wave where it's going to peak here from the standing wave. Now, what's the distance difference here? Is that one of these will have a higher energy because it's basically being over the potential. One of them will have a lower energy because it's peaking over here where it's not the potential. And what that does, that takes our little diagram that is forcibly erased through the limit of black point space on the science center and opens up a gap in it. What that does. If you look at your E versus K, this is no periodic potential. When you put in the actual periodic potential, you pretty much get the same curve, but you're still getting these gaps. So you actually open up these gaps. What they are, they depend on basically the one that has lower energy, this would be the one standing wave here, and then the one with higher energy, this would be the standing wave here. That's actually what's causing that. And what do we call that gap? We call that this is called the band gap. And it's entirely the result of having a periodic potential. Okay, and having those reflected waves and the transmitted waves forming a standing wave depending on the energy that you have. Yep.
So what does the periodic potential represent within the atom?
Of the crystal structure. Okay. So the crystal structure, remember we had the Bravais lattice, we moved over a certain distance here, and then we had the exact same structure.
Yeah.
So it's that Bravais lattice. Now I'm not drawing, that's what I to draw this one here. So I just drew a stupid one-dimensional piece like that.
Mm-hmm.
But it'd be that Bravais lattice.
But doesn't the band gap exist like just for an atom itself?
Not for one single atom.
Okay.
You actually have to have collections of them.
Well, that's, yeah.
You have energy levels coming from those, but that's a different thing. This is actually a whole different phenomenon. That's entirely due to the fact that you have the periodic. Okay. That makes sense? Now, and again, if you take a course in condensed matter physics, it's often the modern name is condensed matter physics. It always used to be called solid state physics, but it went through it wanted a cool, sexy, so it became condensed matter physics. It's just solid state physics. You can actually go through and actually explicitly work this out. It's actually involved, which is why we're not doing it. You take the course in quantum mechanics, it may work out the case here. Is the quantum mechanics of it is beautiful. When you work it out, you see that gap forming. There it is. Beautiful. And then there's other things you can do to aspect of. But You go through and analyze that, all it is the standing waveform. You can have one basically peaking over here, one peaking over here, one has a higher energy, one has a lower energy, and you open up that gap. That's all that is. Okay. Now, what could happen here? We could fill these with particles. So I'm going to draw my little energy bubbles like this in here. Okay. So we said we have a metal, we have an insulator, we have a solid. So we said a metal, what's going to happen here is that we give these names here. This is called the valence band. This up here, this is called the conduction. What's going to happen with a metal here? This valence band, what does not happen? It's not entirely filled with electrons. So in a metal, the band not filled with electrons. Okay, so what does that mean here? I can have basically these particles like here. I'm just drawing spin up, spin down. Yeah. So we're saying we're going to fill up to this level here for no reason. So I said right now there's an electric field. How much current is being conducted? Zero, because we have electrons moving to the right, electrons moving to the left. So particles going this way, particles going this way. The net movement, the charge is zero, hence no current. But what can we do? We can put an electric field on this. If you have an electric field on this, what's it going to do? Depending on the direction of the field, you can take particles here and move them up here, or particles here and move them over here. So let's say I'm going to take particles here and move them over here. So if I put an electric field on this, what's going to happen? And so I'm taking particles here, moving them up here, so you can have this guy.
Draw that energy level, I think easier.
Yeah. I could have made life easier myself, I agree. I have something like this. Okay. Now what happens? Because I'm basically taking these electrons over here. Now what do I know? These are all moving to the right. These are all moving to the left. But what do I know about the number going to the right? More of them. And so now this is going to conduct. Okay. This is why metals conduct. Okay. You basically have the band here partially filled. Now, how do you then get an insulator? So an insulator, you need two things. You need to fill the valence band, and the valence band and
Large energy.
yeah, band gap is large. In that case, valence band is like this. Everything is filled here like this. I'm just going to dot 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 to indicate that it's filled. Big gap here, and I have the next band coming. This is the large band gap. Why does it have to be large? Yeah, because you basically, in order to take the electrons here and kick them up in here, you need a really, really large field to do it, large enough that you're probably in this room. Okay. That'll be an insulator. Okay. Make sense? Then what did we say happens with the semiconductor? It's the same thing as this, but the band gap is small. So the semiconductor has a filled valence band, but a small band gap. So it's going to look just like that, but we decrease this. That, yeah, this. So, then the band gap here. And it's small enough that what can thermal energy do? There's going to be enough thermal energy in the system to take the electrons here and take them up into the state here. So these are going to have levels here as well. So thermal energy can actually pick these up. So this is an excitation. Thermal. So will they just be able to conduct? Some, not the greatest. Okay, but they open up. Okay. Yep.
What happens to the electrons when you expose it to electric field?
Okay, so what would that would actually then give you? You could then, depending on again the thermal energy, one's up here, one's upstairs like this. Okay, one's over here would then kick over to here. Ones that have been thermally excited here are moved over here. They'll conduct, so we'll conduct. Okay, and again, depending on this is going to be thermal energy. If you cool the system down, that's going to drop it off. Okay, that makes sense. Now, this right here would be a pure semiconductor. This is a pure. So this is a pure or intrinsic. If you want a practical device, what do you have to do to these things? Add impurities. You have to add impurities, and that's always what doing. So devices are made by adding impurities. To a semiconductor. And do reagent. Okay, so you're going to have to deal with my wonderful periodic table. Periodic table looks exactly like this. That's exactly what the periodic table is. And we come over here. This is column 3, column 4, column 5. Okay. Right here is silica, and right here is germanium. So these right here, so silica and germanium were historically the two most common. And this side over here, and the 5 here, I don't remember what they all are. I think it's phosphorus. I think there's phosphorus here. I think there's arsenic. don't quote the direction here. I think these are here. This side are, actually, maybe this is Indian.
And you're right, it was supposed
Phosphorus, okay. I think indium is here too. Over here, you can have aluminum, resindium over in this.
gallium right there.
Gallium,
No, gallium's where aluminum is.
gallium is here. Aluminum here. Something like that. Okay. I want to look at these right here. This is where that little cartoon picture comes in. So all I did here was pulled out my old electronics book from when I was an undergraduate, and I found some pages that I could photocopy here. The photocopy quality is, but it's the best I could do. It's the hardest part was these little diagrams are not the greatest. Okay, we're going to look at atomic structure in more detail very soon. But the main thing we need to know right now, we need to talk about the number of valence electrons on these things here. And it turns out that the number of valence electrons are the outer number of electrons. So the number of valence electrons are the outer electrons. For silica and germanium. It is. If I have silica here, I would have the dots here, with my 4 electrons. Germanium, the dots here, they're my electrons. Okay. The column 3 here has 3 valence electrons. The column 5 here has 5 valence electrons. So column 3 elements, 3 valence electrons. So if you're to look at aluminum, you're gonna have 3. Okay. If you look at column 5, have 5 valence. Okay. If you look at arsenic, you have things like that. Okay. So what's going to happen is that if, depending on what you put in here, you change the electrical properties a lot. So this is what happens. We can pure sulfur. What you would have is this. Okay. Now the question is, what happens then if you put in, let's say, aluminum? If you add aluminum, so we're going to add aluminum. That's fine. What's going to happen? We have Si here. We have another Si here. We put aluminum here. 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 Okay. So already there, what did you see happening? Well, what happens here is that you actually have a vacancy. That's going to be a vacancy because there's only 3 valence electrons. When you can actually have 2 there. So I can put another one in here. Another one up here. So on and so forth. Okay. So this is what we have. That makes sense? Now, what would happen if instead I have an electric field like this? If you're this little electron right here, that very little electron here, what would you do? Okay, so the electric field is going this way. This is positive. This is negative. This electron is going to have a force on it this way. This little electron here, or one of the other ones, doesn't really matter. It's going to hop over here and go over to here and fill this. That gets filled. And what does that leave this? That leaves us in the vacancy. So what happened here? The vacancy was initially here. Now the vacancy is here. So which way is the vacancy appearing to be moving? This way, even though the electrons are actually what's filling the vacancy. Okay, so the absence of negative charge is going to appear positive. So the positive vacancies are moving those ways. Once I know the group here, they are called the holes. Okay, so these vacancies, the holes, vacancies, appear to move to the right as the electrons move to the left of the vacancies. Vacancies appear to have a negative charge. I'm sorry, the vacancies appear to have a positive charge. They're called holes. So the vacancies, which act as moving positive charges, are called holes. Okay. And any semiconductor that you dope with something from column 3, since you're going to have holes in it, you call a p-type semiconductor. So any semiconductor doped with 3 impurities are called p-type semiconductors. Hey, why do you think we call p-type? Yep.
I have a question about like the bonds.
Yep,
Like,
yep.
what do the bonds look like specifically around the aluminum?
They're going to look exactly like a regular bond, except you're going to, it's said where you can have 2 electrons. So not, it's sp3 hybridization.
So is the
So in other words, if you were to have Phys will be so you're having sp3 hybridization. Okay. You're going to have an sp3 hybridization happening in the aluminum too. But each of these bonds can actually hold 2 electrons. So what you do is you have the overlap of the sp3 hybridization bonds. Same thing's going to happen in the aluminum. The overlap can actually have 2 electrons in there. But you're only going to have 1 electron in there because of the aluminum. So what that does, that's since you can actually have a vacancy in there, fill up something. That's why it acts like a hole.
so is the aluminum making 3 bonds then and just has 1 unpaired electron?
No, it'll form 4 bonds. Okay, just one of the bonds could actually have 2 electrons. It's only has 1.
But it can form a bond even with 1 electron.
Well, because you're having the hybridization. It has the exact same structure as the silicon. So go in there for sure. Okay. Hey, what do you think is going to happen though if we put in elements from column 5, which have an extra electron? Pretty much the same thing, but we're going to have no vacancies. We're just going to have this small little electron. So if we repeat this with the other case, for purities. So I'm gonna say arsenic. So here's your Si. Silicon. The other silicon is good. Then over here, what I'll do is I'll put an arsenic here. Silicon. Like that. Now what happens is we have this other little electron here floating around. So here's an extra. An extra. Okay. Now, what happens if I then have the electric field here like this? What's this little guy gonna do? Yeah, this one's gonna be, it's basically not really in a bond per se, it's just kind of here there. And so this is gonna float this way here. Float. It's gonna be a force out moving it that way. The negative charges are moving this way. So, the extra electron is moving left. So you're gonna say, yep.
I've got the same question about the bond for this case.
Yeah.
Like where that electron's hanging out.
It's I've never looked at the atomic structure for that one there. Usually what happens though, they're just kind of they're not in the bond per se. Now they're going to be in something. What that's going to be, what the nature of that'll be. I'm not really sure.
Is that a problem? I feel like that violates like previously known.
Well, it's going to violate the stuff that you learned in Gen Chem.
Yeah.
About just the nice pure sp3 hybridization. If you actually go into study bonds, that stuff all falls apart. The bonds get a lot more. They're far more involved than just those little things.
So it can hang out while it's still making 4 covalent bonds.
And what kind of combination can be determined? All right.
What when the electron is going to the opposite way? Why are you going to the negative charge instead of going to the positive charge?
Because I don't know what you're talking about.
Oh.
Okay.
Oh.
Sorry about that. Keep me honest. I was being stupid. Questions for that? So anything you're going to dope with column 5 elements, since they're going to be basically the charge carriers are going to be negative, are going to be called n-type semiconductors. So any semiconductor doped with column 5 elements are called n-type semiconductors. Yeah, that's what you have. Now, how do you actually make these in real life?
Blast them,
What?
shoot it down.
So how are a lot of these things all produced?
A lot of solid state synthesis stuff would be for way too much of the dope. So you have to kind of make it pure and then add it.
Okay, how do you make all the semiconductors that you have the life in? Let's say in a computer. Well, it's usually going to be some sort of vapor deposition. So you're going to have basically some sort of aluminum substrate, and not that at all. It's going to be a solid substrate that you start off with. And what do? You basically have a vapor, basically of silica. And what happens? The silica vapor then basically starts growing like this on the silica substrate. And so you kind of grow these layers. Well, what can you put in the vapor if I want a p-type semiconductor? I have silica vapor there, but then I'd also add aluminum vapor as well. Then what I'd start to do is I'd then start to grow then a p-type semiconductor. Now what I could do is I could get the aluminum out of there, keep the silicon, and then start adding arsenic. Then what am I growing? Now an n-type. So what I'd actually have, I'd have a p-type semiconductor followed immediately by an n-type semiconductor. It turns out that's really important because that's called a p-n junction. I want to show you kind of what's behind that. So when you have p-type Next. N-type. You have a p-n junction. Let's see what the deal is for that. So with that p-n junction, if you look at that little handout, the very back page, which the quality is, that's actually showing the p-n junction. So let's actually kind of draw this thing. So here's our p-type. Here's our. So what do we have here? We have the silica, alumina, silica, silica, alumina, silica, alumina, silica. That. And what do? We have these holes here. These are the holes. And then what do we have over here in the N-type? Well, we have silica, arsenic, silica, silica, arsenic, silica, things like that. And what do they have? They're going to have this extra electron here. If you just have them next to each other, just wait. What will happen naturally? This little electron here is going to go where? It's going to go fill this little guy here. And this little electron here is going to fill this guy here, and this little electron here is going to fill that little guy here. Right? You're just going to triple that. So what's going to happen? You're actually going to get a net negative charge on this side here, because the negative charges are vibrating over here. Both things are electrically neutral. And since this is electrically neutral here, it's losing electrons, we're filling these holes here. This is going to develop a positive charge. Yep.
So like the electrons in the holes annihilate each other and they stay there so that because they can find a lower energy state?
Yeah.
Okay.
Because you're allowed to, you can actually, if there's a vacancy, you can always fill the vacancy.
Right, but even though that like sets up an electrical
Correct.
gradient that would like oppose it.
So what's this going to do? If I start losing if the negative charge goes over here, leaving this positive, if I have negative charge accumulating here, positive charge accumulating there, I'm getting a electric field. So I'm going to get a natural electric field that's going to go like this. And this region right here, there's going to be basically no, there's no net charge here per se. This region here is called the depletion. Now, what would happen if I had another electric field going in the same direction here like this? In other words, I have this picture here. Now imagine, I'll put it up here. Imagine now I have an external field like this. This is an E field like this. So I put a battery. Let's say here's my P-N junction. Here's my P and here's my N. I put a battery like this. So that could be an electric field like this. Okay, what's going to happen?
Where's the electrical going?
This way, in the same direction. What's going to happen to that depletion picture?
Oh, wait, no, please don't say. I feel like, is it like emitting light or something like that? No.
Well, we haven't done those yet.
Okay.
That's what happens if the electric field is going in this direction.
It encourages more electrons to find more holes.
Yeah, more electrons are going to go this way over here. What's going to happen to that depletion region? It's going to get bigger. Okay. Instead, if I reverse this, my P side over here, my N side here, I flip my battery. Now I have electric field going this way. Now what's going to happen? Yeah, and what's going to happen to this depletion? It's going to get smaller. Well, this depletion region here, so what happens in that depletion region, since basically all the vacancies have been filled, that doesn't conduct well. So if that that depletion region gets really, really big, things just aren't going to be able to pass through that easily. And what's going to happen to any current trying to go in that direction is going to be very weak. Okay, because on this side here, that conduction layer, that depletion region is smaller, it's going to be easier for current to actually punch through it. So what's going to happen is that when the depletion region gets bigger, the internal resistance is effectively going up and it's going to conduct very little current. But this depleted region is smaller, it's thinner, it's going to be easier for the current to actually pass through it and have a smaller resistance. And this is called a diode. You have a question, Chase?
So this depletion region, because it's depleting the carriers there.
You have a question?
I was gonna say how, like, LEDs are made of semiconductor, how does it work? And
It's kind of the reverse process with a lot of these things here. So what you can do happen is that you can actually have there's different things you can have. You can have some like light in here like this, and it can kick out a particle and it can be filled that can go off the light. That's how the thing works. There's a lot of different ways. Yep.
What's the typical mole percentage of the purity that thinks
You can put me in a lab and ask me the most remarkably basic.
I've got a graph for you.
And I can actually show, I would not be able to answer anything about that. Okay? You can put me in front of a random piece of equipment and just start telling me what this is and just make up things. Like, you know, right, this is actually where we make the time vortex.
it's like probably not worth that.
Okay, I can actually, if you're asking any practical details on almost anything, I can tell you. Yes,
Can you repeat how like the depletion region grows?
it's basically going in the same direction as here.
Mhm.
So what's gonna happen here is that if you have the electric field like this, it's gonna force the electrons from these regions here. Okay, and these other regions to actually be forced out now. It's gonna force them through here going over here to the south. That makes the depletion region grow. It's basically because it's in the same direction as the electric field.
So if you increase it that way, wouldn't the electrons be pushed towards the positive end, towards the other?
Well, we had this way and then we had this way.
Right.
Okay.
I'm
So
sorry.
we had, it's basically if the electric field is going in the same direction, it's going to
Yeah.
force the electron, it's going to make it bigger. Okay, it's going in the opposite direction, it's going to make it smaller.
Okay, so like we have like the N type, you've
Yep.
got like extra electrons there.
Okay, I went wrong, I'm sorry. Apologize. Go ahead.
And like the inherent
Yep.
electric field setup is that way.
Okay.
So shouldn't it be like pulling the electrons in the N type further to the right?
Okay, so let's see, if the electric field is going this way here, that would make,
So it's going from positive to negative.
no, what I'm saying is right, but I'm trying to come up with a counter for your argument. Right now, I can't think about, let me think about it, I'm gonna have to get back to you on Friday. Okay. But right now, I mean, what you're saying, I understand.